The rivalry between the United States and China may well be determined by computing power. Strategies in Beijing and Washington now realize that all advanced tech, from machine learning to missile systems, from automated vehicles to armed drones, requires cutting-edge chips, known more formally as semiconductors or integrated circuits. A tiny number of companies control their production. That is an excerpt from the book I recently read titled Chip War: The Fight for the World's Most Critical Technology by Chris Miller. Really, it was a great book. Fundamentally, it's about the history of chips and semiconductors and how this plays into the geopolitical power struggles we've seen in the past and how that has led up to our current day. It talks a lot about advanced technology, and I would say takes a specific perspective on microelectronic semiconductors and the impact on defense, especially as that shapes up to form what the author proposes softly as Cold War II, our primary strategic competitor being China. So starting in the beginning of the book, it talks a bit about the basics of computing, what exactly a microchip is, how this technology was created, and then follows it throughout the life cycle of the impact of this technology, the early markets that it was used in, and then how that transformed into the commercial products we see today, the creation of Silicon Valley, all the way up to the present day, and where we are currently at with electronic supply chains and defense and geopolitical power struggles. So the basis of modern computing. At the core of computing is the need for many millions of ones and zeros. The entire digital universe consists of these two numbers. Every button on your iPhone, every email, photograph, and YouTube video. All of these are coded ultimately in a vast string of ones and zeros. But these numbers don't actually exist. They are expressions of electrical currents, which are neither on, 1, or off, 0. A chip is a grid of millions or billions of transistors, tiny electrical switches that flip on and off to process these digits, to remember them, and to convert real-world sensations like images, sound, radio waves, and others into millions and millions of ones and zeros. It was only 60 years ago that the number of transistors on a cutting-edge chip wasn't 11.8 billion, but 4. In 1961, south of San Francisco, a small firm called Fairchild Semiconductor announced a new product called the MicroLogic, a silicon chip with 4 transistors embedded in it. Soon the company devised ways to put a dozen transistors on a chip, then 100. Fairchild co-founder Gordon Moore noticed in 1965 that the number of components that could be fit on each chip was doubling annually as engineers learned to fabricate ever smaller transistors. This prediction that the computing power of chips would grow exponentially came to be called Moore's Law, and this led Moore to predict the invention of devices that in 1965 seemed impossibly futuristic, like an electronic wristwatch, home computers, and even portable communications equipment. It's amazing what Gordon Moore was able to see all the way back in 1965, but it really, the crux of that prediction is his understanding and ultimately development of Moore's Law, that the continued development and innovation in shrinking the number of transistors, shrinking transistors and the number of them increasing that can fit on a single silicon chip was going to unlock tremendous capability that we could not even imagine at that point. Early electric computers used the vacuum tube, a light bulb-like metal filament enclosed in glass. The electric current running through the tube could be switched on and off. A tube turned on was coded as a 1, while the vacuum tube turned off was 0. These two digits could produce any number using a system of binary counting, and therefore could theoretically execute many types of computation. This was a leap forward in computing, or it would have been if not for the moths, because vacuum tubes glowed like light bulbs. They attracted insects, requiring regular debugging by their engineers. It's crazy. This is obviously where the term bug comes from. If you ever have a bug in your computer, if you're ever debugging it, trying to root cause an issue that you're having with your system, it came from literal bugs getting in the original computers. And that's because these original computers used vacuum tubes, and they were huge. A computer could be the size of a room or even a building. This goes all the way back to World War II, when they were trying to decode the German codes to ultimately win the war, and they needed to keep the bugs out of the machines. So scientists at Bell Labs in New Jersey created the first transistor or switch to turn the flow of electricity on and off. William Shockley was among the most accomplished theoretical physicists who took part in this discovery. This occurred in 1948. Fundamentally, a chip is just more than one transistor put onto a single silicon wafer. Invented by Jack Kilby at Texas Instruments during a summer break when other employees were off, he invented the integrated circuit, but it became quickly known as a chip because each integrated circuit was made from a piece of silicon chipped off a silicon wafer. So again, this is where chip comes from. It is because the original integrated circuit was made from a piece of silicon chipped off of a circular silicon wafer, hence the name chip. So this technology is super interesting, but it might not be immediately clear what this technology could be used for, but because you're able to code these ones and zeros in a vast string of binary, it allows for very interesting, complex computations that were not otherwise possible unless they were done by hand. So the early applications actually used to be NASA and the Department of Defense. Of course, they're still both consumers of microchips, but most people don't think of the Department of Defense necessarily, or the government generally, as being the center of innovation, but that is where the early microchip industry comes from. One of the first major customers of Fairchild Semiconductors was NASA, which was critical in helping Apollo get to the moon. The computers that guided the Apollo spacecraft and the Minuteman II missile provided the initial liftoff for America's integrated circuit industry. By the mid-1960s, the U.S. military was deploying chips and weaponry of all types, from satellites to sonar, torpedoes to telemetry systems. Bob Noyce, the future founder of Intel, knew that military and space programs were crucial for Fairchild's early success, admitting in 1965 that military and space applications would use over 95% of the circuits produced that year. The early bombing campaigns in Vietnam, like Operation Rolling Thunder, which stretched from 1965 to 1968, dropped over 800,000 tons of bombs, more than what was dropped in the Pacific Theater during all of World War II. This firepower had only a marginal impact on North Vietnam's military, however, because most of the bombs missed their targets. Texas Instruments knew nothing about designing bombs, so Words, an engineer, started with a standard issue bomb which had already been dropped unsuccessfully around the Ton Ho Bridge. He added wings that could direct the bomb's flight as it fell from the sky. Finally, he installed a simple laser guidance system that would control the wings. A small silicon wafer was divided into 4 quadrants and placed behind the lens. The laser reflected off of the target, which shined through the lens onto the silicon. If the bomb veered off course, one quadrant would receive more of the laser's energy than the others, and circuitry would move the wings to reorient the bomb's trajectory so that the laser was shining straight through the lens. In the early 1960s, it had been possible to claim the Pentagon had created Silicon Valley. In the decades since, the tables had turned. The U.S. military lost the war in Vietnam, but the chip industry won the peace that followed, binding the rest of Asia from Singapore to Taiwan to Japan more closely to the U.S. via rapidly expanding investment links and supply chains. The entire world was more tightly connected to America's innovation infrastructure. Even adversaries like the USSR spent their time copying US chips and chip making tools. Meanwhile, the chip industry had catalyzed an array of new weapon systems that were remaking how the US military would fight future wars. American power was being recast. Now the entire nation depended on Silicon Valley's success. So it's interesting that Silicon Valley was initially a product of defense. It clearly goes the other direction after that, focusing much more on commercial products. We'll talk about in a bit. But I think it's interesting. I think we've seen in the mid 2020s this start to shift back the other way. So we'll see what comes in the future. And the other thing I think is interesting is the ability to take this technology, integrated circuits, from a niche military application to the rest of the world is ultimately what created Silicon Valley. And I think it can be understood as a proxy for how we continue to innovate. I think we should continue to invest dollars. We should, whether it be defense applications or not, but invest dollars in innovative technology, because we don't know when the next technology revolution is going to come. Back to the book. It was the traitorous 8 young engineers who abandoned Shockley's company, as well as a similar group at Texas Instruments, who turned Shockley's transistors into a useful product, chips, and sold them to the U.S. military, while learning how to mass produce them. Armed with these capabilities, Fairchild and TI entered the mid-1960s with a new challenge: turning chips into a mass-market product. So again, the basics of how a chip functions is relatively straightforward. Transistors function as switches to process digital ones and zeros. However, for this technology to be of real value, it has to go beyond bombs and defense products that only have one customer, frankly, the government or our allies. And it needs to be able to compute real-world complex problems. And the technology also had to be small enough so that single computers did not take up entire buildings. So to achieve this, an ingenious technology called lithography is invented. So Jay Lathrop, an engineer at Texas Instruments, is the one that pioneers this. So back to the book. Lathrop covered a block of germanium with one of Kodak's photoresist chemicals that would disappear if exposed to light. Next, he turned his microscope upside down, covering the lens with a pattern. That light would only pass through a rectangle-shaped area. Light entered the pattern, shined into a rectangular shape through the lens, and was shrunk in size by the upside-down microscope. As it focused onto the photoresist-coated germanium, with the rays of light creating a perfectly shaped miniature version of the rectangular pattern. Where light struck the layer of photoresist, the chemical structure was altered, allowing it to be washed away, leaving a tiny rectangular hole far smaller and more accurately shaped than any glob of wax could have been. Soon, Lathrop discovered he could print wires too, by adding an ultra-thin layer of aluminum to connect the germanium with an external power source. Lathrop called the process photolithography, printing with light. He produced transistors much smaller than had previously been possible, measuring only 1/10 of an inch in diameter. Photolithography made it possible to imagine mass-producing tiny transistors. We take for granted, but what comes up here next is the origin of equity offers in tech. So what really serves as the foundation for Silicon Valley technology companies and a lot of startups today is the ability to recruit top talent. And top talent, while they want to work for a meaningful mission and do all of those sorts of things, money at the end of the day is one of the primary driving forces. And one of the best ways that you can offer someone a lot of money is not necessarily in cash compensation, but in offering them equity in the company, especially in ventures early on. This allows employees to participate in the upside, and then it also aligns incentives so that you own the company, you have shares in the company, your work directly results in you potentially profiting from that. And so it creates an environment in which people are much more vested, literally, and they, I think their work reflects that, and it also allows Silicon Valley to recruit the best talent in the world. And this really wasn't the case prior to this. This is sort of an innovation in and of itself. So back to the book. Venture capital funding was pouring into startups that focused not on rockets, but on corporate computers. Fairchild, however, was still owned by a East Coast multimillionaire who paid his employees well but refused to give them stock options, viewing the idea of giving away equity as a form of creeping socialism. Eventually, even Noyce, one of Fairchild's co-founders, began wondering whether he had a future at the firm. Soon, everyone began looking for the exit. The reason was obvious. Alongside new scientific discoveries and new manufacturing processes, the ability to make a financial killing was the fundamental force driving forward Moore's Law. As one of Fairchild's employees put it in the exit questionnaire he filled out when leaving the company, "I want to get rich." I think this is amazing. I mean, it lays it out perfectly, but what this is saying is the driving force of Moore's Law is not a endless pursuit of making technology better. While that's definitely part of it, what's driving Moore's Law forward is that there are a lot of people with incentives aligned properly that will make a lot of money if they can make this technology work. And that employee said it perfectly. I want to get rich. And maybe some people don't say that as bluntly, but I think that's a lot of people's underlying motivation. Back to the book. At Fairchild, Bob Noyce and Gordon Moore were unhappy about their lack of stock options and sick of meddling from the company's head office in New York. Their dream wasn't to tear down the established order, but to remake it. Noyce and Moore abandoned Fairchild as quickly as they left Shockley's startup a decade earlier and founded Intel, which stood for Integrated Electronics. In their vision, transistors would become the cheapest product ever produced. So next, as Intel and other electronics firms are developing semiconductor technology, we start to see the supply chain for this technology move to Asia. And this is really how the electronics industry as we know it today becomes very much Asia-centric. Fairchild was the first semiconductor firm to offshore assembly in Asia, but Texas Instruments, Motorola, and others quickly followed. Within a decade, almost all U.S. chip makers had foreign assembly facilities. Managers at Fairchild had no game plan for globalization. They would just as happily have kept building factories in Maine or California had they cost the same. The semiconductor industry was globalizing decades before anyone had even heard of the word, laying the groundwork for the Asia-centric supply chain we know today. By the end of the 1970s, American semiconductor firms employed tens of thousands of workers internationally, mostly in Korea, Taiwan, and Southeast Asia. The more semiconductor plants on the island and the more economic ties with the United States, the safer Taiwan would be. Taiwan has made itself an irreplaceable partner to Silicon Valley. That's foreshadowing to a lot of things that we'll talk about later, but this, of course, plays very significantly into the ultimate position we find ourselves today with the strategic race against China. So a bit back to the history. After World War II, Japan, of course, is decimated by the atomic bombs dropped on Hiroshima and Nagasaki, but the United States takes a strategic position to rebuild the country and to, of course, rebuild it as a democracy and make it dependent on the United States in many ways so that they become one of our allies and trading partners in the region. And we also start to see how this strategy backfires a little bit, but ultimately resolves itself. So the end of turning Japan into a country of democratic capitalists had worked. Now some Americans were asking whether it had worked too well. The strategy of empowering Japanese businesses seemed to be undermining America's economic and technological edge. This is because many Japanese electronics companies had started to sprout up, and they were doing things at a higher quality and lower cost than many American firms and pushed a lot of American firms out of business. Jerry Sanders, CEO of Advanced Micro Devices, or AMD, had almost died after a brawl on Chicago's South Side at age 18, where he grew up. After his body was found in a garbage can, a priest administered last rites, though he had miraculously emerged from a coma 3 days later. He eventually landed a job in sales and marketing at Fairchild Semiconductor, working alongside Noyce, Moore, and Andy Grove. I think it's amazing how a lot of the main players in this growing market at this time all knew each other, and they all go on to become basically giants in the industry. Japan's semiconductor surge seemed unstoppable. Soon, all of Silicon Valley would be left for dead like teenage Jerry Sanders in a South Side garbage can. Semiconductors are the crude oil of the 1980s, CEO of AMD Jerry Sanders declared, and the people who control the crude oil will control the electronics industry. So why is this even something to be concerned about? Well, at this point, so much of our consumer electronics and United States military applications are dependent on electronics. And if we don't control the supply chain at all, then we're very vulnerable to potential manipulation. And this was the case then with Japan. And we see that play out a bit differently with China, except Japan's ultimately still our ally in this scenario. The U.S. military was more dependent on electronics and thus on chips than ever before. But in the 1980s, the report found around 17% of military spending went toward electronics, compared to 6% at the end of World War II. Everything from satellites to early warning radars to self-guided missiles depended on advanced chips. The Pentagon task summarized the ramifications in 4 bullet points, underlying the key conclusions. United States military forces depend heavily on technological superiority to win. That's still the case now. Electronics is the technology that can be leveraged most highly. Semiconductors are the key to leadership in electronics. United States defense will soon depend on foreign sources for state-of-the-art technology in semiconductors. Japan's advance had caught everyone by surprise. You don't want the same thing to happen to semiconductors as happened to the TV industry, to the camera industry, told the Pentagon. Without semiconductors, you're in Nowheresville. America's supply chain statecraft had worked brilliantly in fending off communists, but by the 1980s, the primary beneficiary looked to have been Japan. Its trade and foreign investment had grown massively. Tokyo's role in Asia's economics and politics was expanding inexorably. If Japan could swiftly establish dominance over the chip industry, what would stop it from dethroning America's geopolitical preeminence too? Again, to the previous point, I think it's really interesting how worried people were at this time because of how dependent we were on Japan, and Japan was our ally. And how worried maybe we should be today is what this book is positing, that we are in a very similar situation with Taiwan / China, and yet they're not our ally. At least Taiwan is, but it's of course at risk because of its proximity to China. So that was the concern in the 80s, but ultimately Japan is overtaken from a production standpoint. In 1993, the U.S. retook first place in semiconductor shipments. In 1998, South Korean firms had overtaken Japan as the world's largest producers of DRAM memory, while Japan's market share fell from 90% in the late 1980s to 20% by 1998. So sort of born out of this era of Japan's superiority is a small win for the U.S., and that's Micron. So back to the book. When two brothers, Joe and Ward Parkinson, founded Micron in the basement of a Boise dentist office in 1978, it was the worst possible time to start a memory chip company. However, Micron's scrappy Idaho engineers outmaneuvered rivals on both sides of the Pacific with their creativity and cost-cutting skill. After a decade of pain, the U.S. chip industry finally scored a win. Another, of course, iconic American firm is Intel, founded by Bob Noyce, like we talked about. However, as most know today, Intel is not in the strategic position it used to be, where it had a near monopoly on electronics. It's now in a position where it's It sort of missed the AI revolution, and it has fallen behind in many other ways. So there's a couple of reasons for this, and we'll talk about a couple stories that kind of got them where they are today. Except for Apple's computers, almost every PC used Intel chips and Windows software, both of which had been designed to work smoothly together. Intel entered the personal computer era with a virtual monopoly on chip sales for PCs. Grove's restructuring of Intel was a textbook case of Silicon Valley capitalism. He recognized that the company's business model was broken and decided to disrupt Intel himself by abandoning DRAM chips it had been founded to build. The firm established a stranglehold on the market for PC chips, issuing a new generation of chip every year, or two, offering smaller transistors and more processing power. Only the paranoid survive, Andy Grove believed. He actually wrote a book called Only the Paranoid Survive, which is very popular. More than innovation or expertise, it was his paranoia that saved Intel. And now into the Soviet Union's role in electronics. The short of it is ultimately they try to copy things, and it never fully can match the innovation that is produced by free markets and capitalism. In the early 1980s, the KGB reportedly employed around 1,000 people to steal foreign technology. The USSR's copy it strategy had actually benefited the United States, guaranteeing the Soviets faced a continued technological lag. In 1985, the CIA conducted a study of Soviet microprocessors and found that the USSR produced replicas of Intel and Motorola chips like clockwork. They were always half a decade behind. Moving forward, the semiconductors' continued role in advanced defense technology highlights American dominance. So fast forwarding a bit to the 90s here. Early in the morning on January 17th, 1991, the first wave of American F-117 stealth bombers took off from their air bases in Saudi Arabia, their black frames quickly disappearing. This is, of course, the Nighthawk built by Lockheed Martin's Skunk Works. In the dark desert sky, their target, Baghdad, the Persian Gulf War had begun. U.S. air power proved decisive in the Persian Gulf War, decimating Iraqi forces while minimizing U.S. casualties. Weldon Word received an award for inventing the Paveway. The Paveway is a bomb, improving its electronics and driving down its cost. As Bill Perry watched the Persian Gulf War unfold, he knew laser-guided bombs were just one of dozens of military systems that had been revolutionized by integrated circuits, enabling better surveillance, communication, and computing power. The Persian Gulf War was the first major test of Perry's offset strategy, which had been devised after the Vietnam War, but never deployed in a sizable battle. So essentially what the offset strategy is that Russia or China have a volume advantage, and they probably always will, just from a people perspective, from a volume production perspective, the ability to throw bodies and throw large amounts of equipment at things or at potential conflicts are probably always going to be their advantage. But what we can do is not focus on matching them there, but to offset that advantage with whatever our advantage is. And our advantage is advanced technology. So in other words, don't try to match our adversary on their strengths, but lean into our own strengths, which are innovation and tech. Back to the book. After the easy defeat of Saddam Hussein's Iraq, America's vast new fighting power was visible to everyone. This caused a crisis in the Soviet military and the KGB, who were embarrassed, yet afraid to admit how decisively they were outgunned. The Cold War was over. Silicon Valley had won. So now to the book, the rise of Taiwan, how electronics come to be centered there, and then why China is left behind initially. The Taiwanese government turned to the person who first helped bring semiconductor assembly to Taiwan, Morris Chang. After 2 decades with Texas Instruments, Chang had left the company in the early 1980s after being passed over for the CEO job. So when the government of Taiwan called, offering to put him in charge of the island's chip industry and providing him a blank check to fund his plans, Chang found the offer intriguing. At age 54, he was looking for a new challenge. Chang pitched a new business model to fellow TI executives in March 1976. So this is before he left. The low cost of computing power will open up a wealth of applications that are now not served by semiconductors, creating new sources of demand for chips, which would soon be used in everything from phones to cars to dishwashers. The firms that made these goods lacked the expertise to produce semiconductors, so they'd prefer to outsource fabrication to a specialist, he reasoned. Moreover, as technology advanced, the cost of manufacturing equipment and research and development would rise. Only companies that produce large volumes of chips would be cost competitive. The Taiwanese government provided 48% of the startup capital for TSMC. From day one, TSMC wasn't really a private business. It was a project of the Taiwanese state. So this ingenious thesis by Morris Chang turned out to be the right bet. TSMC is currently the world's leading foundry or fab, and the US remains a leader in chip design and chip design software, but we're almost completely dependent on foreign foundries like TSMC to fabricate our chips. Hence, Taiwan's massive strategic importance, because while Taiwan is definitely on our team currently, if China were to invade or interfere in other ways, we would essentially be choked off completely from our chip supply. And then back to the book, why China was not able to capitalize in a similar way to Taiwan. Were it not for the communist rule, China might have played a much larger role in the semiconductor industry. However, Mao's radicalism made it impossible to attract foreign investment or conduct serious science. The year after China produced its first integrated circuit, Mao plunged the country into the Cultural Revolution, arguing that expertise was a source of privilege that undermined socialist equality. Mao's partisans waged war on the country's educational system. Thousands of scientists and experts were sent to work as farmers in destitute villages. Many others were simply killed. Now, back into the Intel story, why they were not able to continue to capitalize on their previous success. Shortly after the deal to put Intel chips in Mac computers, Jobs came back to the CEO of Intel with a new pitch. Would Intel build a chip for Apple's newest product, a computerized phone? Cell phones use chips to run their operating systems and manage communication with cell networks, but Apple wanted its phone to function like your computer. It would need a powerful computer-style processor. As a result, they wanted to pay certain prices. The CEO of Intel told a journalist after the fact they wanted to pay a certain price and not a nickel more. I couldn't see it, he said. It wasn't one of those things you can make up on volume. And in hindsight, the forecasted cost was wrong and the volume was 100x what anyone thought. Intel turned down the iPhone contract. This, of course, is just a massive blunder. The iPhone and smartphones generally revolutionized the entire world. It's one of the most popular consumer products ever. So they miss out on the iPhone revolution, and then they also miss out on EUV technology, and then ultimately on AI as well. So back to the book. As the chip industry entered the EUV era, Intel looked poised to dominate. The company has been crucial to EUV's emergence. We'll talk more about EUV, but it's essentially the next generation photolithography technology that allows even more transistors to fit on a single chip. The company had been crucial to EUV's emergence thanks to Andy Grove's initial $200 million bet on the technology in the early 1990s. Now, after billions of dollars of investment, a substantial portion of what had come from Intel, ASML had finally made the technology a reality. ASML is the firm that produces the lithography machines. Yet rather than capitalizing on this new era of shrinking transistors, Intel squandered its lead, missing major shifts in the semiconductor architecture needed for artificial intelligence, then bundling its manufacturing process and failing to keep up with Moore's law. So if Intel wasn't the winner of the AI revolution, despite them being well positioned to do so, there has to be another winner, and that winner is NVIDIA. So the company that eventually came to dominate the market for graphics chips, NVIDIA, had humble beginnings. not in a trendy Palo Alto coffee house, but a Denny's in a rough part of San Jose. NVIDIA was founded in 1993 by Chris Malachowski, Curtis Priem, and Jensen Huang. Huang, who was originally from Taiwan but had moved to Kentucky as a child, worked for LSI, a Silicon Valley chipmaker. He became the CEO and public face of NVIDIA, always wearing dark jeans, a black shirt, and a black leather jacket, and possessing a Steve Jobs-like aura, suggesting that he's seen far into the future of computing. I would suggest learning more about Jensen Huang. He's really interesting, has an interesting story being brought here by his parents, going to a sort of like orphanage school. Just really, really interesting story, and really represents the American dream as well. NVIDIA's first set of customers, video and computer game companies, might not have seemed like the cutting edge, yet the firm wagered that the future of graphics would be in producing complex 3D images. NVIDIA not only designed chips called graphics processor units, or GPUs, capable of handling 3D graphics, it also devised a software ecosystem around them. In 2006, realizing that high-speed parallel computations could be used for purposes besides computer graphics, NVIDIA released CUDA, software that lets GPUs be programmed in a standard programming language without any reference to graphics at all. At the time, Huang could only dimly perceive the potential growth in what would become the biggest use case for parallel processing: artificial intelligence. Today, NVIDIA's chips, largely manufactured by TSMC, are found in most advanced data centers. It's a good thing. The company didn't need to build its own fab. At the startup stage, it probably would have been impossible to raise the necessary sums. So it's so expensive to create your own fab. It's so difficult to produce the chips once they are once you have the fab, that this is why firms like NVIDIA ultimately are just designing chips and releasing software for designing and running those chips. So that's NVIDIA's position. They're designing and creating these next generation chips that are powering things like artificial intelligence, but ultimately TSMC is the one that is producing them. To learn to recognize images of cats, a CPU would process pixel after pixel, while a GPU could look at many pixels at once. So the time needed to train a computer to recognize cats decreased dramatically. NVIDIA has since bet its future on artificial intelligence. From its founding, NVIDIA outsourced its manufacturing largely to TSMC and focused relentlessly on designing new generations of GPUs and rolling out regular improvements to its special programming language called CUDA. That makes it straightforward to devise programs that use NVIDIA's chips. As investors bet that data centers will require ever more GPUs, NVIDIA has become America's most valuable semiconductor company. This book came out in 2022, but that's certainly still the case. That trend has continued. I think if you would have taken action or invested and bought NVIDIA at the time this book was released, you would have done quite well. Back to ASML, the company in the Netherlands that produces the lithography technology that the foundries, the fabs, need to produce the chips. Back to the book. The next generation of chip production and lithography will require ever smaller features to be carved onto the chips. This necessitated extreme ultraviolet light, or EUV. However, the manufacturing of EUV wasn't globalized, it was monopolized. A single supply chain managed by a single company would control the future of lithography. ASML. This is pretty crazy. There may be other examples of this that I'm not aware of, but this is like a single company that basically controls one of the most important industries on planet Earth. Back to the book. The most crucial input into a EUV lithography system wasn't any individual component, but the company's own scale and supply chain management. ASML engineered this network of business relationships like a machine. ASML rewarded certain suppliers with investment, like the $1 billion it paid to Zeiss in 2016 to fund the company's R&D process. This is a company in Germany. It held all of them, however, to exacting standards. If you don't behave, we're going to buy you, ASML CEO Peter Wennink told one supplier. It wasn't a joke. ASML ended up buying several suppliers after concluding it could better manage them itself. Now, back to China building up to what is softly proposed as a Cold War II. As the decade ended, only two companies could manufacture the most cutting-edge processors, TSMC and Samsung. And so far as the United States was concerned, both were problematic for the same reason, their location. Now the entire world's production of advanced processors was taking place in Taiwan and Korea, just off the coast from America's emerging strategic competitor, the People's Republic of China. Which core technologies most worry Xi? Xi's the leader of China, essentially their dictator. One is a software product, Microsoft Windows, which is used by most PCs in China, despite repeated efforts to develop competitive Chinese operating systems. Yet even more of Xi's thinking are the chips that power China's computers, smartphones, and data centers. As he noted, Microsoft Windows operating system can only be paired with Intel chips, so most computers in China needed American chips to function. So in many ways, we're going through this strategic analysis of our vulnerabilities and the concern with China. China's doing the exact same thing, and their concern and reliance on American products. In many countries, it's impossible to use a phone without using some of Huawei's equipment. As difficult as it is to use a PC without Microsoft products or surf the internet outside of China without Google, however, Huawei is different from the worlds of other big tech companies in one major way. Its 2-decade-long struggle with America's national security state. So I'm probably mispronouncing this, but Huawei is a major Chinese technology firm. Meetings with foreign companies and governments were more pleasant when everyone pretended that cooperation was win-win. So Washington kept telling itself that the U.S. was running faster, blindly ignoring the deterioration in the U.S. position, the rise in China's capabilities, and the staggering reliance on Taiwan and South Korea, which grew more conspicuous every year. One U.S. semiconductor executive said to a White House official, "Our fundamental problem is that our number one customer is our number one competitor." Huawei was simply cut off from the world's entire chip-making infrastructure, except for chips that the U.S. Commerce Department deigned to give it a special license to buy. Nevertheless, it's surprising that China has done nothing to retaliate against the hobbling of its most global tech firm. It has repeatedly threatened to punish United States tech firms, but never pulled the trigger. So the government essentially banned Huawei in the United States because of the strategic vulnerabilities it produced by having us rely on their technology. But what this is noting here is that China has not necessarily done similar things to our technology firms. They have definitely stolen our country's and our company's IP. They have definitely copied things. They have definitely pushed people out of markets, but not in the same way that we did with Huawei. Key chip makers from America's Intel to Taiwan's TSMC have now cut off the Kremlin. Russia's manufacturing sector has faced wrenching disruptions with a war between the US and China. Wrenching disruptions with a substantial portion of Russian auto production knocked offline. The emerging Cold War between the US and China, however, will be a less lopsided match when it comes to semiconductors. Given Beijing's investment in the industry and given that much of the chip-making capacity America relies on is in easy range of PLA missiles. PLA is the army of China. It would be naive to assume that what happened in Ukraine couldn't happen in East Asia. Looking at the role of semiconductors in the Russia-Ukraine war, Chinese government analysts have publicly argued that if tensions between the US and China intensify, they must seize TSMC. Cold War I had its own standoff over Taiwan in 1954 and again in 1958 after Mao Zedong's military barrage of Taiwanese-held islands with artillery. Rather than a standoff over an impoverished island, this time the battleground would be the beating heart of the digital world. So this book is really framing Russia certainly as a threat because of their aggression in Eastern Europe, but China is the true risk, the true potential peer, and that's because of their proximity to Taiwan. That's because of their own dominance in technology, whether it be from copying us or not. They are growing and are set to be on a path to become a peer in a way that Russia maybe necessarily isn't a technological perspective. And also, China has been straightforward about their desire to reunify Taiwan with the Chinese mainland, and of course that's not coming from Russia. In conclusion, here, back in December 1958, an electronics conference took place in a wintry Washington, D.C. Attending that day were Morris Chang, Gordon Moore, and Bob Noyce, who all went out for beers, and then, in the day's waning hours, meandered back to their hotel. Young and excited, singing amid snowdrifts, no one they passed in the street would have guessed these were three future titans of technology. Yet they've left an enduring imprint, not only on billions of silicon wafers, but on all of our lives. The chips they invented and the industry they built provide the hidden circuitry that structured our history and will shape our future. That is the end of my notes on the book. Again, the book is titled Chip War: The Fight for the World's Most Critical Technology by Chris Miller. And it's a great book. There's much more that I didn't cover here. But thank you very much, and Deo gratias.